90. A particle of mass m kilograms is suspended in equilibrium from a point A on the ceiling of a room by a light spring of natural length L meters and modulus of elasticity 2 mg newtons. A. Show that the extension of the spring is L over 2 meters. And that's for 2 marks. Hello everyone, I hope you enjoyed my last video on the inclined plane. This video is about springs. Well, if it's about springs, we use Hooke's law. First thing we do, spring question, Hooke's law. What is Hooke's law? Hooke's law states that force is equal to K delta L, where F is the force stretching the spring, K is the spring constant, and delta L is the amount the spring has stretched by. So for example, suppose you've got a spring constant of 10 newtons per meter. That means it will take a 10 newton force to extend it by 1 meter. If you've got a spring with a spring constant of 20 newtons per meter, then 20 newtons is required to extend it by 1 meter. And this is how we choose our spring constant. The larger the spring constant, the stiffer the spring. However, for our question, and in this course, we don't write Hooke's law in terms of a spring constant, which is the normal thing to do. We write it in terms of the modulus of elasticity of the spring. And the modulus of elasticity has units of newtons, only newtons. So our expression for Hooke's law now becomes F is equal to lambda, where lambda is the modulus of elasticity multiplied by delta L over L, where delta L is the extension of the spring and L is its original length. So the modulus of elasticity doesn't tell us specifically how much the spring will extend with a given force. It tells us its fractional increase. So for example, suppose we've got a spring and it has got a modulus of elasticity of 20 newtons. This means 20 newtons is needed to double the length of the spring, or to extend it by an amount equal to its length. So if you've got a 20 newtons, say, if you've got a spring of a modulus of elasticity 20 newtons, and we apply a force of 10 newtons, then it will extend the spring by half its original length. And that's our problem here. We are told the modulus of elasticity is 2 mg, where mg can be anything. When we come along with a force half of that, then clearly the string is going to extend by half its amount. And to find that out, just put the values into the expression and you'll find that you get the answer that's needed. A second identical spring is attached to the particle and secured to a point B on the floor of the room. B is vertically below A and the distance AB is 3 L meters. A. Given that both springs remain in tension when the particle is again in equilibrium, find an expression in terms of L for the extension of the original spring, and that's for 4 marks. So now we have a mass attached to a spring and the spring is hanging from the ceiling. I'm going to call the first spring L1 and it's extending by an amount equal to half its length. But we come up to another spring, identical in properties and identical in length, and we attach it to the mass and we pull the mass down until the spring reaches the floor, and we attach the spring to the floor and we just leave it. Now we're told that both springs are in tension. This means both springs are being stretched. Therefore, the upper spring is pulling up on the mass and the lower spring is pulling down on the mass. Because the earth is also pulling down on the mass, we have a situation where the mass is being extended, where the extension of the upper spring has been extended by a wee bit more. We can see that from the diagram. And we're also told the important fact that the two springs were extended has a length equal to 3 times the original length. Now you might be able to see intuitively then that delta L1 plus delta L2 has to be equal to the length of the spring. A good diagram will also help you get there. That's your first expression then. That will be useful or essential. This mass is in equilibrium. That means the forces actually on the mass have to add up to 0. Newton's first law. So that what we have here, we've got the upper spring L1 pulling up on the mass, and we've got the lower spring pulling down on the mass, and we've got the weight of the mass also pulling down on the mass. And these three forces have to add up to 0. So that's our two expressions there. We've got our force expression and we've got our geometric expression. Delta L1 plus delta L2 is equal to L. And remember L1 plus L2, remember L1 and L2 have the same value to be equal to L. When we do all that, we've done the physics and the rest of it and mathematical manipulation to get us the result that we want. And this short clip here illustrates that. Stop at any point you want to see what the steps are, but I'm sure you'll be able to follow them anyway. Well, I hope you enjoyed the video. If you did like it, give it a like or subscribe. Or if you have any questions or suggestions, please ask. Meanwhile, I'll work on another video and I should have that up very, very shortly. Once again, thanks for watching the Unsquared Physicist.